unmuted and camera switched off actually for better connectivity. So very warm welcome to everyone. On behalf of Institute of Indian Foundrymen Chennai chapter, extend a hearty welcome to all the delegates joining us today for this technical webinar on Elkem's ingenious solution for increasing ductile iron casting yield. Moving forward, I request our chapter chairman, Mr. P. Sendil Kumar, actually to deliver the welcome address.
Good afternoon, fellow Foundrymen. On behalf of the Institute of Indian Foundrymen Chennai chapter, I extend a warm and heartfelt welcome to all the participants joining us today for this technical webinar on Elkem's ingenious solutions for increasing ductile and casting yield. First and foremost, I would like to thank all of you for taking the time for joining this knowledge sharing session. As we all know, the foundry industries today faces increasing expectations regarding resource efficiency and sustainability. This improving casting yield has therefore become a strategic lever to reduce melting energy, conserve raw materials, minimize rework, and enhance overall profitability. To set the context, ductile iron has achieved remarkable growth globally due to its outstanding strength to weight ratio, toughness, elongation, fatigue resistance, machinability, and cost effectiveness. And it continues to replace cast steel and forged components in many engineering applications. To improve the casting yield, this ductile iron has a direct impact on reducing melting energy, improved material utilization, lower scrap and felting loss, higher consistency in microstructural and properties. And today we have a privilege to have with us Mr. Balaguru Sendil, a well-known gentleman in the foundry industries, Deputy Manager R&D TCS Foundry Elkem Innovation, as our guest speaker. Elkem has been our pioneer in inoculants and melt treatment, alloys and process metallurgy, and delivering tangible improvements in scrap reduction, structure control, and casting yield across the global foundries. I'm sure this today's session will gain invaluable perspectives, metallurgical insights, and practical improvements to strategize can help us our foundries become more competitive, efficient, and sustainable. I encourage everyone to participate actively, ask questions, and make this interactive learning experience. I would also like to take the opportunity to thank our annual sponsors who play a vital role in enabling us to organize various technical programs that benefit our members throughout this year. Additionally, a special appeal to our Chennai chapter members. As you all know, we'll be celebrating our 40th chapter day, the Ruby Jubilee year, on 24th November at Hotel Ramada Park in Kandy. We kindly request you to enroll in large numbers for the morning technical session, participate actively, and make this milestone events truly memorable. Once again, warm welcome to all of you. Wishing you the engaging and enriching technical session. Thank you. Raj, over to you.
Thank you, Sendil, sir. To move forward, actually, it's my pleasure actually to introduce today's speaker, Mr. Balaguru Sendil, Deputy Manager R&D and Technical Customer Service, Foundry Division at Elkem Innovation. Mr. Balaguru holds his BTech and MTech degree from Shastra University, specializing in foundry alloy production, in addition to a specialized diploma in automation from Sweden. He is a qualified research professional with 10 years of applied experience in ferroalloy development, foundry metallurgy, and cast iron metal treatment technologies. At Elkem, he is part of the global foundry innovation team and also serves as a technical customer service manager for India. His key area of expertise includes thermal analysis of cast iron, metal treatment solutions for SG and CG castings, process optimization using statistical tools, defect analysis of cast iron, and foundry automation. He has delivered technical seminars across multiple IEF chapters, including Jalandhar, Belgavi, Indore, Jamshedpur, Jaipur, Rajkot, Kolkata, Chennai, and Coimbatore. He has also conducted customer training programs for several leading Indian foundries, such as LMW, Synergy Green, HL Mando, CAE Automotive, Madras Engineering, SFL Autoleg, and others. With deep technical knowledge and rich field experience, Mr. Balaguru brings valuable insights into foundry process improvement and metal treatment optimization. We request actually Mr. Balaguru Sendil to move forward actually with the presentation.
Hello.
Yeah. So.
Yeah. Good morning. Good afternoon, everyone. Thank you for the warm introduction. introduction, and I would like to thank each and every one of you for being here, taking the time out on a weekend, and I hope I will be able to add some value to your time here. I would share my screen now. Hope it is visible.
Yeah, I can go to presentation mode.
Yes.
Yeah, yeah.
Okay, the screen is visible. I have the presentation mode on. And as rightly summarized by our IF Chennai chapter president, casting yield for ductile iron is something which is getting very critical these days. And I would like to use this session to talk about how we can improve it. There are quite a few opportunities here for us in the Indian foundry sector where we think we'll be able to add significant value in the process so that the casting yield can improve significantly. So in this session, I'm going to give about a few details related to metals, especially where Elkem is involved, its products and services, so that we will be able to add a better product as well as a better service to the foundries in India. So today we will talk about in the agenda, if you look at, we will talk about the need for casting yield optimization and how we go about optimizing it. That is with respect to the base chemistry of the metal that we are going to have, with respect to the nodularization process, and with respect to inoculation. So there are other aspects as well that I would touch upon, but we are not very keen on that because we don't have that much expertise when compared to nodularization inoculation. We are quite depth field knowledge is there with Elkem. So before I begin, as a customary, I always share my screen with share my slides, and I have the presentation. What you see here is not my work. It's a combination of Elkem team. It's a combination of what's available online platform, and we have a very strong technical team in Elkem where we interact frequently, discuss problems across the globe, so that we will be able to have deliver the best value to the Indian foundry sector. So the problem what we are facing is not only limited to us, it's a global challenge. And sometimes we might do things which are much better than what globally standards follow. So it gives us a nice platform to share knowledge, gain knowledge, and then deliver the same to our customers. So I would move forward. If I look at it, what is the need of the hour? We have seen a very stable growth rate for India. And in our recently in Elkem, we strongly believe that the Indian foundry sector is the only one which is growing very aggressively. There's a huge demand for castings. There is uncertainty with tariffs looming around, but having said that, there is quite a strong demand from the local as well as export market. And on an average, compared to China is huge, but India is also equally on par when it comes to developing critical components. So the trend areas, what we see in Elkem is the automation and digitalization that is going to drive the foundry moving ahead. There's going to be a lot of casting simulation adaptation. Many big foundries have started adopting it. Small foundries have started adopting it as well. They see a value in it. And also, they are going to go for certain systems which can predict are defects, which can predict mechanical properties so that they ensure quality assurance. Not only curtail to quality control, but we are moving a bit ahead with digitalizations, artificial intelligence to have a better prediction of what's going to happen. In foundry terms, we are using thermal analysis for it. It is a very nice tool to see, measure how much is your metal quality and predict certain parameters. And then we are also as seeing there's a good capacity expansion happening. Foundries are slightly expanding. A lot of high pressure molding lines are being added. And this being said, especially for auto components, people who are moving from conventional RPA to high pressure lines, the casting yield is going to be a very critical impact because high pressure molding lines are quite stringent when it comes to casting yield. The methoding and gating has to be very strict. It's not as convenient as a conventional line where you can change the methoding or it is very flexible that way. But when it comes to high volume production, it is preferred to go for automation solutions. So high pressure molding lines, when you go for it, casting yield is of extremely important. And when you take sustainability into focus, as our chapter president touched upon it, green foundries are going to be very keenly monitored by the OEMs as well as by the government. So there's going to be a lot of recycled material that is going to be pushed into our foundries, be it scrap or be it more of materials that are not used by other industries, pig iron, waste material. We need to find an efficient way of consuming it. There's going to be a lot of emission norms which is going to kick in. and how we are going to tackle that. So these have been the trends. And if you look at the challenges, Foundries is always challenged. We don't have a very fixed raw material. Our material cost keeps varying. We use somebody else's waste. At the same time, our energy demand is quite high and uncertain. The environmental regulations are there. There's always a labor shortage when it comes to having skilled labors, people who can make sure that the foundry is running consistently. The process controls have always been slightly here inconsistent because of inconsistent labor market. At the same time, with the development of automation and digitalization, this is something that could be sorted. There's not that much of a technology gap when it comes to ductile iron in India. We feel that when I at least personally go around India looking at people making ductile iron castings, the basics of fundamentals of how to make ductile iron has been very strongly developed in the Indian market. And it is not that we are doing over engineering. The Chinese market is very simple. It is over engineered market when it comes to gating and methoding and casting yield. The casting yield is the secondary priority there. The game for them is volumes and turnover time. So at least in India, we are not following that footstep yet. Not across sectors, at least in certain critical sectors, we are very strong when it comes to technology. We understand the significance of casting yield. We understand the significance of having good metallurgical process control and good product. So this has always been the challenges. Competition is also there. Competition among Indian clusters is also quite heavy. Coimbatore is competing against Rajkot or vice versa when it comes to certain segment of pump castings. So how do we differentiate is the challenge. And we are quite confident when it comes to how we approach the solutions. With our solution is to focus on lead time. When it comes to developing a certain casting, you need to be quick. We focus on casting yield. Casting machinability improvement is also quite stringent when it comes to having this competition. You have to have competitive pricings. For that, you need to focus on almost all areas, as well as the service life of a casting, which is something gaining more traction in India market. What do I mean by service life? How long the casting can perform. Is it mandatory to replace a brake drum or a brake disc after 25 or 30,000 kilometers? Why can't we have it more? So this is the approach in which Elkem works. And for today's session, I would going to be focusing more on casting yield. And there's a very important picture I have put here. It's called value. What do I mean by that? It is something what you gain extra out of what you pay for. So you might buy a product or service, but that the amount you pay is only what you get for the product, what additional you get. And this is very important. Value management is going to be very keenly monitored in Foundry, not only for the top management, but for the employees also. So an employee who can deliver more value to his or her organization is going to be very strongly secured in the future. No AI, nobody can replace that person. So we need to understand what can we do with respect to value generation. So this is the need for the hour. We are seeing quite a strong demand, to summarize, in the Indian market with automation and digitalization coming in. Capacity expansion and sustainability in focus. The more important is to focus inward into a foundry to secure our business, our volumes in this tough, challenging market. Which could last for a few years now with the market US tariffs. So how we are going to go about it? So casting yield is something that is one of the areas where a foundry, ductile and foundry, can focus, because 1 or 2% saving in casting yield will result in savings up to lakhs. Even for a very small foundry who's making 200 tons of castings per month, if you are able to save 1 or 2% in casting yield, at the end of the year, your savings will be in lakhs. So it is very, very important we focus on casting yield. So why casting yield? It basically reduces your production cost. More saleable casting, more money made. It also reduces waste when it comes to unwanted melting. Less fuel is consumed, less peddling, energy saving is there. It improves your productivity. You no need to have for higher capacities. You want to do an additional 10 tons, 15 tons here and there, then it can be easily managed. It more or less, very important point here is it improves your casting quality consistently. And this is the point I would like to insist in this session. How do we make sure that we are able to make castings with fewer defects consistently and effectively? It also improves your competitiveness. So this is a very nice summary I have put here, courtesy of AIs. But how do I go about achieving all these things? So casting yield, we know that it is very important. I can save money. I I can have higher capacity. At the same time, my money is saved, so I'll be more competitive in the market. But if I'm able to improve my casting quality also, which is an added advantage with casting yield optimization, then I'm in a better position. So it is rather easier said than done. So how do I do it? So there are quite a few ways in which it can be done. The first thing is to introduce technology. We are having foundries who are using casting simulation softwares. They are able to optimize both the gating as well as the risering technologies to an extent where they see predict defects and ensure that whatever methoding and is being developed is accurate. This is not always the case for everybody. Some people are doing it as a consultancy. Some people have bandwidth to buy a software and do it. And at the same time, it also depends on how good the person who's developing the methoding. There are many guidelines, there are many books and knowledge sharing sessions available by other suppliers of the software simulations who are able to give very good, much better than what I would be able to do with respect to gating and risering design. I will touch upon these two things. And the most important part I would like to discuss here is the graphite management. So when we say about improve casting quality, there is something called as to optimize your gating. We need to look into the graphite management. What do I mean by it? It is the ability of us to control the carbon which we have in our metal. We are ability to control when the carbon is going to come out, how it is going to come out, either graphite or carbide, and in what stage it is going to come out. If you are able to balance this, then the need for bigger risers and bigger gatings can be eliminated. If you are able to eliminate the need for these two things, then automatically you will be able to save on your casting yield. So I will discuss about improving casting quality and graphite management in this line. Moving ahead, as I told, gating is very simple. You have the metal, you need to have a path in which the metal is filled a particular cavity and ensures that you don't have any improperly filled cavities. So here there are a few objectives. If you look at it, they don't want to have fading. You need to have a very turbulent pouring. And the target here is also simple. You need to maximize your casting yield. So this has been very fixed design. It depends on your pressure. It depends on your type of molds. It depends upon your sand system. It depends upon your casting profile, many things. The thing I would like to focus when it comes to casting yield is to have for risering. The objective, one of the objectives of risering is to have shrinkage elimination. Unlike steel, which has a very limited expansion capacity, so the ductile iron tends to shrink a bit more. So we need to compensate for it with additional metal present, so that whatever volumetric shrinkage which is happening towards the end of solidification is compensated by the metal which is coming from the riser which feeds it. There are multiple types of risers available in the market. We have normal, pressurized, and the list is endless. And what are the challenges we see from Elkem is that most of the time it is over-engineered. Why it is over-engineered? Sometimes because of process inconsistencies, people tend to keep slightly bigger risers so that the effect of shrinkage is eliminated or it is being pushed towards the riser. Do we really need to do that is a question that we need to ask continuously, because we are, yeah, sorry. Because we are more or less focusing towards riserless designs. This is not suitable for all. I understand it is for certain types of casting, certain profiles of casting where the modulus is small or the geometry is in such a way that the modulus cannot be too big. But this is a very good system that is being developed, a riserless design. But one of the key points for it to have a riserless design is to have the highest metallurgical quality for the liquid iron. So this again pertains to graphite management. I would touch upon this with our inoculation and nodularization topics. And at the same time, the temperature must be not more than 1300 degrees Celsius. So to have this sort of targets, which is going to be the future of ductile iron foundries in India, to be effective and competitive in the market, we need to have a shift in our mindset that do we really need to use a bigger riser? To solve a casting shrinkage issue, I can add one more riser. Is a very simple solution that foundry people adopt. I understand it is quite quick and time saving. You are able to ship out the casting fast. But I would not stop there. I would suggest or request the team to focus on why do I need to add another riser? How can I eliminate it? And why did the shrinkage happen at the first place is something that an RCA should be properly done. And I think you can approach us, or you can take knowledge from this upcoming slides on how we can optimize it. So gating and risering. Gating is very simple. The objective is to fill the metal as fast as possible, as not turbulent as possible, and ensure there is no gas defects. And here, when it comes to risering, shrinkage elimination, and we should opt for very small risers and see if there's a possibility to eliminate it completely. Not for all castings, certain castings, then that's a very effective solution what we have. It is not very simple, but it is possible. We are seeing quite a few foundries in India as well as abroad who have adopted to very minimum risers as well as riserless casting designs. When it comes to graphite management, there are three important points here. The three important areas to manage graphite. If you are able to manage the graphite properly, because graphite, when it comes out, it gives heat. So the natural shrinking of metal can be compensated. So it is very, very important that you are able to control when is the carbon coming out of graphite at what stage. If you are able to do these two things, then you can actually have a very small riserings designs in your castings. To do that, the most critical is our pouring temperature. It must be as low as possible. Make sure that it doesn't do a collapse. Apart from that, you should keep it at a very optimal temperature. We will touch upon that. The second thing is the chemical composition, which is with respect to carbon equivalent. The most important point for shrinkage reduction is you're having the correct carbon value and the silicon value. This more or less for the particular casting section thickness or the solidification rate determines how much of a risering design is required. So the carbon equivalent selection is very, very important. There are a few guidelines which I would like to show in the upcoming slides. At the same time, a very important process is of nodularization. It is a process where we convert a flake to a nodule. I will explain that. At the same time, inoculation. So if you are able to optimize these three things in a way that you are able to manage your graphite more effectively, how do I manage it? I will explain in the slides. How do I measure it? A thermal analysis is a very good tool of measuring. So if you have a correct temperature, if you have correct chemistry, if you have very good nodularization process and minimum or good inoculation, then your casting yield can definitely be improved. Up to 5 to 7% yield improvement is possible. So that is huge savings for a casting, huge savings for a foundry. Even couple of castings that they make large volumes, if they're able to take dedicated projects, then we will be more than happy to help in these lines where we feel we will be able to add more value to the customer. So I would touch upon before jumping into carbon equivalent. We have seen this slide. You are pouring metal, it is getting solidified. There are two primary elements that we are going to focus. One is carbon, silicon, manganese, sulfur, and phosphorus are also considered primary elements in ductile iron. But I'm more interested to look at the picture down. It's a very nice picture of high nodule count of very small uniformly distributed nodules. This is something that we would like to target. If you look at it, this carbon is quite an interesting element. It can form in different shapes and combines that I have explained in various sessions. But here I would like to mention here is that carbon can come in different forms. Hence, it's an allotrope. It can be a carbon, it can be graphite, it can be diamond, it can be carbide, whatever. But in foundry, we are more interested only in graphite. So what happens? How is this formed when the metal is being filled? You have something called as solidification happening. So why do I need to understand solidification for casting yield optimization? Because this is very, very important. We talked about graphite management, and the graphite management begins with solidification. So what do I mean by solidification? People who are in shop floor might have seen when the metal is in liquid state, there's always something growing from the middle or from the side, and it is branching out and towards trying to form something. That is something called as a phase transition. It is not a transformation, it is a transition from one state to another state. It's not a very drastic thing that is happening, change happening. It's a sequential stage, hence transition. It is from a liquid to a solid. It is called as solidification. When does it happen? When your temperature is below a certain point. How does it happen? It is having a nucleation growth phase. So there's something called nucleation. So which is nothing but a point on which the metal begins to solidify. So more of nucleation points, more of solidification points, then the casting can cool in a better form. So this is what with respect to solidification, nucleation is very important. Your chemical composition, your nodularization process, and your inoculation will determine how much of this nuclei is available for good nodule formation. If you have less nuclei, then you have problem, more nuclei, which is also going to be a very good microstructure Very too much is also a problem. So this is very important to understand that carbon is very important for us. At the same time, we would like to control the shape, the profile, and the timing, how the carbon is growing with the help of chemical based chemistry, with the help of inoculation, and with the help of nodularization. And we are also having other elements, which there are something called copper, tin, moly, nickel. These are alloying elements. Then we have trace nodularizing elements. I have put here magnesium, cerium, and lanthanum are called as nodularizing elements. I will touch upon this later. And then we have something called inoculating elements. Nodularizing and inoculating elements need not always be the same. These are different elements which helps in inoculation. So these are very two distinct process which should not be interlinked or it should not be mixed for an understanding. This has to happen very separately. Then only you'll be able to have a very good metal. When you have a good metal, you can have for small rises and casting yield can be optimized. So solidification is very important. And with respect to solidification, we have seen this diagram. It's quite scary diagram for people who are new in the foundry. We have iron carbon diagram. So in this iron carbon diagram, I would like to quickly show about certain factors or certain parameters which are important to us. The first is going to be graphite. We want the carbon to come out as graphite, which is stable. We don't want carbides, which is unstable. And the first thing I would like to show here is that we are only concerned anything beyond this particular point. Reality, how much of carbon we have is mentioned here, somewhere between 3.3, 3.2, 3.4 is what we have. At the same time, I would like to also show about what is austenite. So if you look at the picture here, it is nothing but it is the first ion that is formed when the metal is cooling down. It is like a tree-like branching structures. So when you are having a different carbon equivalent, when you are having on the hypo side, which is this is the center line, which is a eutectic line. So this is an eutectic line. The green line, what you see is an eutectic area. It is not just a particular value, it is a range. It's not 4.3, it is actually a range. So what is austenite? We saw it is the first thing that is to form. It is the first metal. When the metal is cooling down, it is something that the first thing that grows is austenite. Then you have eutectic, and then you have something called as graphite here. So if you are having your base metal with the correct chemical composition, and if the transformation is happening at eutectic, you have both the austenite and graphite growing parallelly. If you are having on the hypo side, you have first the austenite growing. If it is on the hyper side where the carbon is more, then first the graphite comes out. It is not the austenite. So this actually very important to understand this, because it kinda influences how the casting is being solidified and the graphite management. And high hypereutectic cast irons determine or requires a different kind of risering systems, a different kinds of inoculation practice when compared to a hypo or eutectic. It is very subtle changes, but if you are able to measure these changes and able to control it, then you can very much optimize your risering to bare minimum levels, which is again the ideal zone in which we would like to operate. But typical, most of the ductile iron foundries operate in the eutectic region of 4.3, where you have first the transformation happening. The liquid is transforming into two solids simultaneously. So we have both the austenite and graphite growing. And then when you have further, it cools down, the austenite interlinks together and then forms a very nice microstructure. In case of when you are looking at the hypo composition, you have first you have your austenite growing, and then you see the black torch graphite growing, and then they join together, and then the microstructure kinda looks different. I will show a much better picture to visualize this. And then when you are in the hyper region, you have first your nodules, which is, sorry, you have first your graphite that is coming out, and then you have the austenite agglomeration around it, and then finally you have a microstructure like this. When the metal is cooling down from normal pouring temperature of 1400 to our room temperature till about 700 degrees Celsius, you have this process happening. The eutectic happens about this particular 1145, 1146 degrees Celsius. And then you have something called eutectoid, where you have the austenite that you formed earlier will again break into two different components. It could be either ferrite or perlite. Ferrite is nothing but the austenite transformed. It's from one structure to another structure it has transformed. If it is, I have put a picture of here, this is a fully ferritic and it's a perlitic grade. It has a different hardness. Austenite, when transformed to ferrite, is slightly soft. When you have more perlite, it is more hard. And this actually determines the grades and applications of the cast iron. So I would like to change here is that FSM and inoculants play a major role here in this graphite management. So your FSM is also having silicon, your inoculant is also having silicon. So we need to understand that having more of inoculant, having more of FSM is not always ideal, because it will influence the carbon equivalent. It might change the casting from this to this or from this to this, which is not very an ideal situation. So as I told earlier, carbon equivalent is very, very important when it comes to casting yield optimization, because the carbon equivalent can move the liquidus temperature by up to 300 degrees Celsius. What do I mean by that is that when the metal begins to solidify, it can go up to either above 300 or below 300 degrees Celsius. So it plays a very, very vital role. Correct carbon equivalent also reduces the need for over inoculation, because I have heard people saying that I need to add minimum 0.5, 0.6 of inoculant, otherwise I'm not getting mechanical properties. So sometimes I wonder it is because the inoculant, it's good for us, we sell more inoculant, but it is not a required process. It is because of the inoculating elements, or it is just because of the silicon, or it is because of some other elements that is coming with the inoculant, they are preferring it. So we need to understand this. Overdoing is not always ideal. If you look at the microstructure, when you're having hypo, the image kind of looks like this. The eutectic is something very ideal. We have very small uniform size nodules distributed. When it comes to hyper, you see slightly bigger nodules, primary graphites. Because here the nodules kind of prime graphite comes out first. This tends to get overeaten, and you might see in areas where you don't have that much amount of any forms of graphite here. And when you have this sort of micro, it's very sometimes possible in certain solidification rates to have shrinkages. So it is not always ideal to keep the carbon on the higher side. Increasing the carbon beyond certain limit for your particular casting section thickness will also result in shrinkage. Which is the correct to keep carbon equivalent should be based on your section thickness. So thin section typically go for higher carbon, and then the carbon equivalent is also high. Thick section we go for low carbon equivalent. In thick section, to avoid shrinkage, if you're going to keep 3.6 or 3.7 carbon, then it is all going to join together, become hyper, and because of very slow cooling solidification, it is going to get exploded, and it is going to have a different mechanical properties. And if you take a sample out of it, it might not have the required mechanical properties. At the same time, if it is a load bearing area of the casting, it can prematurely fail, which is not a very ideal situation. So again, we have multiple grades of cast iron. So when you are going to look into selection of carbon and selection of carbon equivalent, you have to ideally refer to what is the section thickness you are having, what is the minimum and maximum, and select the correct carbon value for your casting. Do not go for high just to solve the problem of shrinkage, or do not keep it too low because you want to have not so high. You are getting very low mechanical property, so you keep the carbon low. It is also not a very, very kind of an ideal situation. So if you look at it, we have multiple grades. Just to recap of it, we have these are conventional grades. We do have other grades. We have CMO, SSF. We have high temperature wear resistant grades, which is not discussed here, but I thought I should mention generically that why do we have multiple grades and how these grades are formed. The carbon equivalent, what you see here is with respect to all the grades. When it comes to selecting which grade is required and how do I control it, it is mostly these elements. It is with respect to the alloying elements. So we have perlitic grade, which is having very high strength and good wear resistance. Basically high strengths like 800 bar 2, 700 bar 2, 600 bar 3. And then we have a mixed matrix of ferrite and perlite, and then you have very ferritic grades. The ferritic grades are having a very good elongation and impact resistance, good thermal conductivity, but they do not have very high strength. They are quite soft, but at the same time it is more elongated, malleable. So these sort of grades can be linked to here, but we are having unique grades where we have high strength as well as high elongations. That is being practiced very commonly here. Elkem has done a lot of technical literature as well as paper published on it. If anybody is interested to know more about, do let us know. We will be more than happy to develop certain grades which do not fall within this particular slide's purview, where we have high silicon and low carbon kind of grades. Then the carbon equivalent slightly differs. The methoding and risering slightly differs for that. The treatment of inoculation as well as nodularization is also different for that. I just would like to highlight here that when you are going for high silicon grades, you have to be very careful. High silicon means SSF kind of grades. You have to be very careful with respect to your FSM or nodularization as well as inoculation. Already the silicon is high. If you add overdosage, then you might end up getting a lot of shrinkage related issues, a lot of carbides and very poor mechanical properties, or the casting would be extremely difficult to machine. So if you're facing these sort of conditions, do approach us. We will be more than happy to help. So with respect to carbon equivalent, we have touched upon it. We need to have the current carbon equivalent. Having always high is not a very ideal situation. As a thumb rule, I don't believe in thumb rules, but to some extent, to have knowledge shared here, a 3.6 is a very good carbon equivalent to begin with for castings. If you're having big castings, if you're making certain 30-40 ton kinds of windmill kinds of castings or slightly heavy castings where the solidification rate is very slow, you can make a 100 kg casting solid box with a very slow solidification rate at the center, or you can make a uh, you can make a very thin casting which cools very badly, or you can make a very thick casting which cools very fast. It all depends on the profile, the chilling methodology involved. So we have to also correlate this whole thickness with the solidification, the rate of solidification. So that much knowledge, I think it is available in the market. If you have any doubts with respect to how do I select the correct carbon equivalent, let me know or let us know anybody in Elkem. We'll be able to happy to guide. So this is with respect to the composition, carbon equivalent, and I told I'm going to touch upon nodularization. Nodularization is a process in which you convert your flake to a nodule. How do I do about? I have certain active elements, magnesium, cerium, and lanthanum. These are used to convert a flake to a nodule. How does it does the job? I have put here a slide picture. You have a very nice optical microstructure here, H1. You see it is at 100x. If you magnify further down, you always see it is some sort of sulfide core with the hexagon shell. The hexagon is important because graphite is also quite a hexagon shape. So when you have an hexagon shape here, it can stack one top of the other, or it can stack like this, or it can join like this and form a plate. So these are the two growths in which a particular nuclei can grow. This nuclei is always non-metallic, MgS, magnesium sulfide, in case of ductile iron. So to make this nuclei, magnesium sulfide or magnesium oxide, with recent developments in nucleation theory, we see magnesium nitride is also very important. So magnesium nitride, all these are the nuclei, non-metallic, but it's all magnesium or cerium or lanthanum based. So this is the process of introducing magnesium to a metal to convert a flake to a nodule is called nodularization. What it does is that the magnesium what you add eats up with the sulfur, oxygen, basically nitrogen that is available in the metal, and forms magnesium oxide, magnesium sulfide, magnesium nitride, multiple components which are non-metallic, and becomes a nuclei, becomes basically a point in which the carbon can come, deposit, grow, and form a nice nodule. So this is the process of nodularization. The most important element is magnesium, cerium, and lanthanum. The first ductile iron was experimentally made with cerium, but due to commercial viability, magnesium is being more or less prioritized and commercialized to a far extent. How do I introduce these elements? I can either use a very pure magnesium and plunge it across, or I can go for ferrosilicon based magnesium. I can go for a mesh metal type to have magnesium introduced for the process of nodularization. Multiple options are available, but the key takeaway here is that magnesium is not very good when it comes to the casting properties. These are extremely carbidic. If you take this particular image on the extreme right corner, after ductile iron treatment, you have just created the nuclei. You don't have any nodules formed. It is more or less full of carbides. After ductile iron treatment, you can pour a sample before adding inoculant and see how much of nodule count you have. You hardly tend to see nodules and full of carbides. So magnesium is a very, very strong carbide promoter, and it should be kept to the bare minimum possible. Keeping more magnesium is not advisable. It is going to cause a problem. With respect to carbides, when you have more carbides and poor nodule count, it is going to cause shrinkage. So magnesium, the only advantage, it can convert a flake to a nodule. Basically, it adjusts the speed in which this axis, the C axis and A axis grows. If this particular chart towards the extreme right, you see the C axis and the A axis here. If this A axis is growing much faster, you typically form a flick. But if the C axis growth is more faster, then you form a nodule. The flick kind of joins together to form a nodule. So naturally, it is the A direction is more easy to grow because of the height difference. It is more easily can joint. But to make sure that the C is growing, you need to introduce magnesium, which modifies the surface tension and make sure that the nodule is being formed. So in this slide, the key point here is that magnesium is a good element to convert a flake to a nodule, but it is very strong carbide promoter and very strong shrinkage promoter. So we should keep it to the bare minimum possible. In the this one, I'm going to talk exclusively about the role of magnesium here. How do I keep this in the nodularization process? Because as we discussed, high magnesium increases the risk of shrinkage and carbides. So typically we in Foundry use optical emission spectrometer. After ductile ion treatment, we see how much is the magnesium. We have a thumb rule that being quite strongly followed, I should have minimum 0.030, 0.035 or 0.050, depending upon the foundry and depending upon what they are making. But do we really need to understand what we are talking when it comes to this magnesium, and why should I have this much amount of residual magnesium? When I know that magnesium is going to cause a lot of carbides and shrinkage, why should I keep it on the higher side? We have challenges with respect to that. I will address that. Why it is so carbidic? Because it's very quick to start boiling. If you try to have people who are using pure magnesium converter process might have seen it reacts very violently with a lot of fumes. Magnesium starts melting at around 900 degrees Celsius, boils at 10,000 degrees Celsius. So when you are tapping at 1480, 1500 degrees Celsius, the reaction is going to be very violent. Most of the magnesium that you add in case of pure magnesium, it is going to go out as fumes. You need to force the reaction. You need to force the magnesium to go into the metal and then do the process of desulfurizing, deoxygen, form magnesium sulfide and oxide. Most of the magnesium would be just wasted in fumes. So that is MgO. So the very important for us to understand how much should be the residual magnesium. So as I told in the previous slide, the nodularizing elements are cerium and lanthanum as well. Be it any nodularization process you use, it could be FSM, it could be cold wire, it could be pure magnesium, it could be in mold treatment. There is always rare earth attached to it. Very few cases where you have zero rare earth based nodularization process. So it is better to add all these three things and then see how much is your residual Mg required. It basically says that how much ever is your final sulfur into 3 times is what I should have my magnesium. So basically when people say, or when the common narrative, I should have minimum 0.030 residual Mg, it is being estimated that you have a sulfur of 0.010. So the relationship between magnesium and sulfur is very important. So when you have very low sulfur and high magnesium, that again is going to cause a problem. Vice versa, when you have also, that's going to create a problem. I will explain what is the ideal sulfur level and what happens when you have mismatch in the upcoming slide. But here I would like to stress here is that magnesium must be kept as low as possible. Magnesium must be kept as low as possible. It is highly shrinkage and carbidic in nature. It reacts very violently. It creates a lot of fumes and dust in the shop floor, which is not again going in favor when the trends that is seen in the foundry. We don't want to have that. We want to have very little smoke. And if you are using high magnesium, you're going to burn a lot of magnesium, waste a lot of magnesium, because making magnesium is quite energy intensive. If a foundry does a proper CO2 calculation, if you use more amount of FSM or high magnesium process, your CO2 will go for a toss. The carbon footprint what you generate is going to be drastically affected. Again, circling back, when we say that I need 0.025 or 0.050, what does this particular value mean? So when you are measuring three things combined, one is your dissolved magnesium, that is certain amount of magnesium is going to get dissolved, like how you add salt to water, the salt gets completely dissolved, but after some point the saturation limit is reached and it starts throwing out. So this dissolved magnesium is something that is not of very use to us. If you take 0.0325, maybe 0.005 could be dissolved magnesium. And then you have magnesium, which is actually forming these micro inclusions. which is in this particular area of the graph. These are very small, 1 micron, 2 micron. This is basically MgS, magnesium sulfide and magnesium nitride nuclei, very small, very stable. And then we are also having magnesium, which is free, MgO based slag flotation. So after ductile ion treatment, deslagging is very important. People tend not to do deslagging because the temperature drop is going to be there, but it is always advisable to keep the to do deslagging. An idle foundry would keep the furnace, keep the treatment ladle for 30-40 seconds after treatment idle and remove as much slag as possible before pouring. If you're going to have temperature loss, then that's a different situation, different case, and we need to find a way to isolate the temperature loss, which also we will talk about later. But the magnesium, what you measure here is a combination of three things. We have dissolved, micro, and slag. The slag is of no use. It is quite bigger and it keeps floating out. You can see the image here. You take a ladle, you take the sample from the top, it is going to give you always high magnesium, but what actually inside is different. So when you're saying in the top, I'm having 0.030, I'm having excellent microstructure, it doesn't necessarily mean that the ladle throughout is having 0.030. The bottom could be much lower. It depends on the type of nodularization you are using. It depends upon how much magnesium you are using to achieve it. So when you are using higher grades of, when you're using 25%, 30% magnesium to make ductile iron and you are getting 0.048, most probably all you are measuring is all the sluggish MgO, which is quite big and floating up. And with this, you might not get very good microstructure. You are prone for shrinkages, you are prone for carbides. At the same time, when you're using a very, very low magnesium, 6% or 4-5% magnesium FSM, and then you're going to have a residual Mg of 0.030 and you get excellent microstructure, then we need to understand that what we are measuring is what is not an actual representation. The magnesium level is much lower, but if you are able to ensure that whatever magnesium you are measuring is mostly in this micro inclusion category, then you get the best result. To achieve most of the magnesium in micro inclusion category, you should use extremely low grade of FSM with low magnesium. You no need to go for higher FSM. You no need to go for higher treatment processes. Then it is very, very difficult to actually get residual Mg, which is very representative of what is there inside. So do we really need to have minimum 0.030 is the question. It doesn't always necessarily need to have 0.030. It needs to be correlated to the sulfur what you have. It also needs to be correlated to the subsequent inoculation that you're going to do. So the key takeaway here is that magnesium is not good. It should be as low as possible. The magnesium you are measuring is three things. It is dissolved. It is a useful magnesium, which is the micro inclusions, and it is also the unwanted magnesium, which is basically larger micro inclusions called slag flotation. So we need to ensure that we are having a very good, calm treatment process. In that case, you will have more of your magnesium in micro inclusion compounds, which is of beneficial. As I told, with respect to shrinkage, magnesium is highly shrinkage, and for when you are having a higher residual magnesium of 0.045 or 0.050, then your probability of having shrinkage is very high. So you need to have compensation with additional risering or slightly bigger risering in your casting profile, which is not in a very ideal situation. If you look at it, 0.02 to 0.04 is an ideal range when it comes to shrinkage. We don't want to go beyond it. If you look at the casting modulus is also quite important. This is in centimeters, so we typically operate in this to this region. You have nothing more than 0.04. This is an ideal range to operate. These are charts prepared by both Sorel Metal and other organizations, very reputed, paper published almost good 20 years back and still holds its value. So the magnesium must be very, very low. You don't need to have high Mg, especially if you're going for high pressure lines, high pressure molding lines, these are Sinto, whatever it is, then if you're having operating at high pressure, if you're operating at higher levels of magnesium, then the possibility of having draws, the possibility of having shrinkage and carbides is very high. When you're having low residual Mg, it is very easy to inoculate. If you're having high residual Mg, you need to have more inoculation. It basically indicates your process is unstable. The only correlation we need to take with respect to magnesium is the microstructure. When you see this sort of a microstructure where you have CGI formed, that means that the magnesium has faded. A nodule has been broken and then it has come back to a vermicular structure. This happens when you have the magnesium is fading. Also, it doesn't only happen because of magnesium fading, it also happens because of high sulfur. When your sulfur is very, very high, then you in that localized sulfur pickup is also possible because we have sulfur pickup from the sand. It could be on the outer surface of the casting. Sometimes it could be collected slightly in depth of the casting. So the sulfur is also very important. If you are having consistently operating at a residual mg of 0.035 to 4, and suddenly you are having in particular day of compactedness in your microstructure, I would focus more on what happened. Is there a sulfur pickup by mistake in the base metal itself, or is there a sulfur pickup from the sand or coating, or is there a high titanium contamination either from the pig iron, from the recarburizer, or from the coating or whatever? So this is the area I would like to focus. If you are having only these sort of a microstructure, vermicular structures, then that indicates the magnesium has been faded or something has happened that the magnesium has become ineffective. The magnesium fades very, very late. You do not typically see ductile iron fading for 12 or 13, 14, 15 minutes after treatment. It is not from the point of tapping. After treatment, people pour for 12, 13 minutes. The pouring is only restricted because of the temperature loss is so high that you need to have, you might end up with cold labs. The fading is very, very not so high. It is quite stable. In the previous slide I showed, the micro inclusions are very stable, 1 micron in size. They do not fade with time. You just need to activate that micro inclusion, which is very small, like the small dot, to a very respectable size nodule of 20 to 50 micron size with correct inoculation. So most of the time, what we see here when people complain about your magnesium or the magnesium has faded, 80 to 90% of the time, it is either because of sulfur or it is because of sulfur pickup from sand, or the interesting reason, it is because of inoculant that has faded. This sort of a microstructure is very good example of the inoculant fading. So the residual magnesium, what do we measure? The residual magnesium has to be directly correlated to nodularity. Nodularity is nothing but the effective measurement of how round is a particular nodule. So this, the pointer image is a nice nodule where if you look at both the shape, it is a very nice round shape and the size is also quite respectable. Whereas the one above it, the size is okay, but the shape cannot be considered as a perfect round. We doesn't match the farad diameter. So this destruction, okay, in shape can be attained or attributed to both inoculant as well as FSM fading. When you have this sort of a fading, it is more or less an inoculant that has not been able to ensure the roundness. Whereas when you have a vermicular structure like this, it is the inoculant and the magnesium both has faded. This is only possible in certain extreme conditions where you pour for long, or when you are having a residual magnesium of 0.035 with majority of the residual magnesium measured being free Mg. This could be the case when you are using 9-10% FSM grade, and then you are having a bare minimum addition rate of 0.8 or 0.7. You maintain a residual magnesium of 0.04, 0.035, and still end up getting poor nodularity, or you end up with getting a high shrinkages. That means that you are on the wrong track when it comes to having FSM and when it comes to having FSM measured. This is a problem that you see in most of the times when you are having higher amounts of free magnesium. When you have higher amounts of free magnesium, you might get this image of diffuse shrinkage. You might this image of very, very small dots, which you don't see in normal microstructure, but this will result in very bad mechanical properties. Your elongation will not be achieved. And if you are unfortunate and it is high magnesium you are having and you have very turbulent pouring, then the possibility of dross is very high. So dross is something that is formed inside the mold when the metal is being poured into the mold, and the time it is being formed or solidified in the cavity. If there is some sort of sluggish generation because of either high oxygen and high magnesium, then it is called dross. They typically tend to have long filamentous appearance. So this dross is a very, very classic example of magnesium being on the higher side, especially the free magnesium. And slag is also quite possible, and then carbides. So when you keep the magnesium higher, these are the problems that you might get. Not always, but quite high. And when it comes to casting yield optimization, this is a very dangerous image to have. So the shrinkage, if it is small, it is okay. It can be managed to some extent. But if it is quite big, then you need to go for compensating with a rice ring. Or you need to put a chill. Chill will not solve the problem of shrinkage. It will just going to move it to somewhere else. So one of the major reasons when it comes to nodularization and magnesium is that you must keep it as low as possible. Operate it with bare minimum levels. Achieve your residual magnesium using very low magnesium, so that whatever you are measuring is of useful micro inclusions rather than free magnesium. When you are having that, then we can definitely work about having your yield being optimized. Ductile and treatment process efficiency, this is something low versus high. Reaction should be calm as possible. The above said factors, how do I achieve it? When you are having a very calm reaction, you don't want to have a very violent reaction. If you have a violent reaction, more fumes, spillages, some foundries I have seen, if I account for spillages, that itself will be 1 or 2%, which is huge money that is wasted as spillages. Then you have slag and fume generation, which must be very low. You don't want to have high slag and high fumes generated. The reaction violence, when it is calm, typically you tend to see very little slag as well as little fume. And then the magnesium recovery, the useful magnesium that you want, it should be always on the higher side. You don't want to have very low magnesium recovery. And then whatever magnesium that you're using should have some inoculating effect. We will touch upon that. It should be also on the higher side. If I take this as an axis, then I would like to be somewhere here where I have high inoculant effect, I have high magnesium, I have very low slag, and then I have very low reaction violence. So if I plot it, I have pure and then high. It just is very simple. If I have converter, I have very not the George Fisher, we have pure magnesium converters. These are used for certain applications. Then we have cold wire, then we have sandwich, then we have tundish, and then we have in mold. So you can see the in mold is the most efficient way of doing ductile iron treatment. But the drawback is that all the casting needs to be inspected 100%. Few foundries are doing it in India, but there's quite a strong demand for that in American market, and American foundries are actually using a lot of in mold FSM. When it comes to tundish, it is having a proper pocket, and a tundish cover is one of the ideal ways where you can have very low reaction violence, high magnesium recovery, and then very little slag fume generation. So I would focus my effort on having in this particular region where I use the extremely low magnesium alloys. So when it comes to low magnesium alloys, again, the selection is very important, because if you look at it, commercially, there are more than 200 plus FSM grades available. When for nodularization, FSM is a very ideal process still. It is the most interesting and relevant process we have, and the most economical process we have to make ductile iron consistently of consistent quality. So 200 plus grades are there. So when we are going to select which is going to be the best for me, we need to look into 3 or 4 major factors. What is the magnesium level? What is the rare? What is the calcium? Sir, I'll take questions at the end. So
आपण भेटलो तुम्ही कॅस्प्रो तो त्यावेळी तुमच्याकडे दिसायला आलो इचलकरंजीमध्ये घरी.
Navle sir, you're on. Okay. So 200 plus FSM grades are available in the market. When we select the selection factors, how do I select which is the best grade for me? What should be an ideal magnesium level for my FSM? What should be an ideal calcium level for me? What should be an ideal rare earth level for me? The 3 important factors to select an FSM are your sulfur. How much is your sulfur content? If your sulfur content is less than 0.015, you have to go for a less than 0.7, 0.6, 0.5 mg containing FSM. If your sulfur is on the higher side, then you can go for 8 or a 9% grade. The 9-10%, 8 or 9, 8 and above percentage of FSM should only be used when you are having not good sulfur control. Sometimes you might end up getting 0.018, 0.020 in your charge mix. Then you can go for higher magnesium FSM. Again, when you do this, majority of the magnesium, what you are going to do is going to be desulfurizing. Magnesium is going to tie up with sulfur, form bigger slag and float out. So in you're using 9%, your residual mg, what you're measuring of 0.035, in that majority of it would be the free mg. Whereas when you are having less than 0.015 sulfur, correct amount of sulfur in your base metal, and then you are using a 5% magnesium FSM and still getting 0.035, then majority of the magnesium what you are measuring, it is going to be a very useful impact, and that for that very minimum inoculation will give you excellent microstructure with high nodularity and nodule count. Not only that, the nodule count what you see will also be small and uniformly distributed, so which is a very ideal situation. So sulfur should be the major reason to determine how much magnesium should I want. If the sulfur is more than 0.040 is what we have put, but typically in Indian condition, if it is more than 0.020, we ideally prefer desulfurization. So this is the case when you're doing duplexing, bringing metal from cupola and then pouring, then ideally we would recommend do desulfurizing before doing ductile ion treatment. The next is having the rare earth being selected. Rare earth is also very important. All FSM will have these three values: magnesium, rare earth and calcium. Not only FSM, you can go for code wire, you can go for other process which will also have these elements present. How much should be your rare earth level? What should I select it? Because this FSM what you are having can have 5% magnesium and then have either 0% rare earth, 1%, 3%, multiple combinations are available. But to a foundry, for me, which should I select? So this rare earth is directly related to your scrap quality. What do I mean by that? How much is the trace element present in your metal that you know from your base metal? If your base metal is having higher amount of trace elements, or you can take a management decision, I'm going to purchase this scrap which is having slightly higher trace elements, and for commercial reasons I would like to use it. But these elements like titanium or boron or arsenic or lead is going to cause a certain problem in my microstructure. How do I neutralize it? In that case, I can go for an FSM with rare earth in it, which is going to primarily solve the problem of having tramp elements from the charge. So your selection of rare earth is very, very correlatable to the steel scrap that you are using. And the last is the calcium. Calcium is very important. It is very correlatable to your tapping temperature. If your temperature is very high, you need to have high calcium in your FSM. Calcium basically calms the reaction. When the reaction is calm, as I told earlier, you have better magnesium in the form of magnesium inclusions, useful magnesium, rather than being wasted. So a calm reaction is ideal. To have a calm reaction, the tapping temperature must be low, but unfortunately, due to my layout constraint or my present process is not good, or I don't have a ladle preheating setup, then I might need to have a 20-30 degree increase in tapping temperature as a flexibility. So in that case, should I go for a slightly higher calcium alloy? 7% magnesium, 1% rare earth, maybe 2 or 3% calcium, which is going to be of beneficial in that situation. If I have an open treatment, should I have the calcium more? So these are some of the questions that I want the foundry persons to think. So this is something when you select an FSM, when you buy an FSM, or when your management asks what sort of an FSM that you would like to know, please relate to this point. So when it comes to yield improvement, a low mg FSM is always preferred. So I put this as a question. I would explain why. When you keep the magnesium lower, we have discussed earlier that you have less shrinkage tendency and less carbides, less formation of slag and dross. So no need to go for additional filters, big rises, direct impact on casting yield. When you are having low mg, it is very easy to inoculate. You have high nodule count as well, which again is going to reduce your shrinkage. This is basically what we have discussed is graphite management. So the microstructure management, what we discussed earlier, to have it in a practical terms in foundry variables, the magnesium is a key important factor. It directly affects your nodularity. To have a better nodularity shape, you need to keep the magnesium low as possible in relation to your sulfur. So the sulfur is something, as I told, very important. The base sulfur should be between somewhere between 0.012 to 0.015. 1.5 can be up to 1.6, 1.7 is acceptable. 1.6 is also okay, but if you keep increasing the sulfur, then you cannot operate at a residual magnesium of 0.033 or 0.035. You need to increase your mg also when the sulfur goes up. There are two options of doing it. Either I can have a high mg alloy and then I will bring down the sulfur, or I go for a low mg alloy with higher additions. So both is not preferred. It is better to have the sulfur in control so that from an yield point of view, you have a very stable process. So you have to select your raw materials. You have to select your recarburizers in such a way that your base sulfur doesn't cross this particular limit. If you are having very high mg, and right now if you are having operating at 0.01516 in that range and using 8 or 9 10% magnesium alloy, most of the alloy, the magnesium that you are having is going to eat up the sulfur, desulfurize it. You will end up seeing very small final sulfur in your base. In your final residual sulfur will also drop. So after ductile ion treatment, from base to final, you see a drop in sulfur. The drop in sulfur also has to be very minimum. If there is going to be a drastic drop in sulfur, that also indicates that most of the sulfur, most of the magnesium what you have used is just done desulfurization. It has not been useful for creating nodules. It has just done desulfurization. So which is also not a very ideal case. So that is why when you are having higher amounts of magnesium, FSM with high magnesium, you keep using it at higher addition rate, then your base metal will eventually lose sulfur. When you have very low sulfur, then that is also very tricky problems you will face. You will end up with getting full amounts of chunky. You will have end up getting exploded. These sort of problems will come. So it is always better to have a correct range of sulfur. A low Mg alloy will not drastically drop your sulfur. Your sulfur level is maintained in the foundry. When you have a consistent sulfur and your sulfur drop is also not significant, you have a very good microstructure here. You see a base sulfur of 0.01 and then you have a final. This is the output. There is not that much amount of drop between base and final. The sulfur value is the same. That means that in the 0.030, most of it has been converted into MGS, which is very small, and it is measured as a part of in the final sulfur. Whereas in this case, the 0.2 that is being measured, most of it is just the free sulfur that has gone out. At the same time, this has been quite insufficient. So this is very, very important to understand that the sulfur, we have to keep it as an ideal range. You have to use an FSM alloy with about 6%, less than 6% at 1.8, 0.9 addition rate. And your desulfurizing after your FSM treatment should not drop way beyond. It can drop 2 or 3 points, not more than that. If it is dropping, that means that I am wasting a lot of my magnesium in desulfurizing process. So this is the key for me to work out. Why am I wasting a lot of sulfur? Why my FSM is being used as a desulfurizer? Is it because of the pocket? It is because of the high tapping temperature. It is because of the ladle temperature. These are some of the questions. You can think about it, but when you want facing these sort of challenges, approach such, we from Elkem or we will come and actually assess these are the parameters what we look out for. And if most of the time we see an opportunity to improve and we drastically improve it. The quickly rare earth is something that we see here. Rare earth, why do we have rare earth? As I told, it neutralizes trace elements, and rare earth is nothing but cerium plus lanthanum mostly. In case of FSM, the cerium is very, very fade resistant. Okay, so having rare earth not only is beneficial to neutralize the trace elements, at the same time it also forms nuclei. The nuclei which it forms is very, very stable. You take this Foundry one, have a residual magnesium of 0.040 and a cerium level of 0.007 versus a Foundry 2, whereas a magnesium of 0.030 and 0.015 cerium. This is more stable. What do I mean by it? The cerium 0.015 will not going to fade for a longer time, meaning as long as the metal is liquid, this is not going to fade. The nuclei it has created, the ductile ion nuclei it has created. You just need to activate it to grow to a correct shape and size by correct inoculation. So the cerium is very, very important. You should have an FSM ideally with cerium, a rare earth in it, so that you are having a fade resistance also there. At the same time, it neutralizes tramp elements. The negative side is that the most common what we see in the industry is that I have cerium, then I have chunky. I will get chunky, I love chunky. That is a common thing that is being communicated in the industry, which is also in a way correct, but not correct. What do I mean by that? When you are having more magnesium and rare earth and the sulfur level is 0.015, but in this case, if I take the Foundry one, the magnesium is 0.040 and the cerium is 0.007. So here, if the sulfur is low, then I might end up getting this sort of a microstructure chunky. Here 0.030, and if the sulfur is balanced, then I would get a very good microstructure. So the problem here is that when I am having more magnesium and more rare earth, and then I have very little sulfur, then I will end up getting chunky. If I have more sulfur and then I have very little magnesium and rare earth, then I will end up getting CGI. As I discussed earlier, sulfur is also very important. If the sulfur is too low, 0.006, 0.007, then it is not an ideal situation. You will end up getting problems of chunky. If the sulfur is too high, 0.020, 0.01817, and then you might end up getting CGI. So a rare earth, it is very important. It neutralizes the trace elements from your melting charge. At the same time, it is more fade resistant. So which FSM should I select? If you're having poor melting charge, what do I mean by poor melting charge? If your trace elements are high, then I go for greater than 1% rare earth FSM. Make sure that my magnesium is not 0.040, my rare earth is 0.015. If I add both of these two, and then I'm getting 0.045 as residual magnesium plus cerium versus a final sulfur of 0.006. That's a very disastrous case for having chunky. So if you're having poor melting charge and high rare earth in your FSM, then you need to ensure that you have correct sulfur also. And when you're having long pouring, you don't have the problem of having poor melting charge. I have decent charge. I don't have that much of trace elements, but I have operating at 0.025, 0.03 residual magnesium. And my sulfur is about 0.010 in final, but still I'm having fading because my pouring is quite long. Then I would suggest, instead of increasing the FSM addition or going for a higher grade of magnesium, I would use the same grade of magnesium, preferably at a lower addition rate, and have the rare earth in the FSM increased from 0.5 to 1, from 1 to 2. This is a step that is quite unique. It is a step that is very common in most of the MNC foundries who operate in India. The FSM that we supply to them always have high rare earth and low magnesium. So this is and most of the foundries who operate in Japan and Europe typically follows this. When to use a less rare earth FSM is only when you are having heavy thickness, very slow cooling, very slow solidifying, heavy section castings, where the rate of cooling is very slow. Inevitably, the nodules are going to join together and going to form an exploded, or possibility of chunky is there. Then I go for a less than 0.5 or less than 1%, 0.1 rare earth FSM. Or when I have very pure metal, I know that the metal is extremely pure. I don't want to have more of nodularizing cerium and lanthanum. Then in that case, the possibility of chunky and exploded is high, so I don't go for it. So ideally, I would prefer that this is the situation in which we operate long pouring. Heavy thickness is only certain foundries in India who make windmill and then who make big ductile and pipe fitting components. But most of us operate in this particular long pouring. In this one, so 1% or greater than 1% rare earth and FSM is always ideal. So if you take it, the ideal combination is that I have a 6% magnesium. I have about less than 0.1 rare earth is very rare. 0.5 rare earth is okay. If I have 1 to 3% rare earth with 6% magnesium, is an ideal. Less than 6% is an ideal combination for casting yield point of view. The last is the temperature and the calcium. So the temperature, as we discussed, the temperature must be less. It must be as close to your pouring, but unfortunately, because of how far is the ladle from the pouring, do we have to have a tundish which needs to be removed? Is the temperature loss high? Then we need to have high tapping temperature. If the tapping temperature is high, then the possibility of you using low magnesium FSM is not going to happen because the burning effect is high. So you need to go for a higher magnesium. So my focus here is that how would I get the tapping temperature lower? If I have high tapping temperature, I need to have more cover scrap. The reaction is violent and fast, low yield. Maybe it is suited for bigger temperature, bigger treatments. Not ideally. We have foundries in India who does 30-40 ton metric tons of casting, who takes 6-5 tons of treatment, and they still use a 5% magnesium. So it doesn't break the myth. It breaks the myth that saying that if the treatment is more than 1%, 1 metric ton, I need to have high tapping temperature and higher magnesium. No, it is not the requirement. You need to understand, we need to understand that I just need to make sure that my temperature loss in the ladle is not high. So what do I need to do to ensure that the temperature loss is not there? Either I have a better insulation or I go for a ladle preheating setup, because the upside when I have both this ladle preheater and insulation is quite high. I can go for a low magnesium FSM. I can compromise. I can take the advantage of having smaller risers or riserless design. I can have lower addition rate of this low magnesium FSM. My casting yield is high. So the costing, if you back calculate it, the value is much higher. So again, the temperature low is an ideal one. When you're having calcium, as I told earlier, calcium calms the reaction. So if you're having 1% calcium, the reaction kind of starts at 25 seconds, gets over. When we're having high calcium, the reaction is calm, more reproducible reactions. So when you're having high tapping temperature, maybe higher calcium FSM. If an open treatment, higher calcium. If you're not going to do deslagging, because calcium when it is high, it is going to give slag. So if you're not doing deslagging, then I probably will have very low calcium. So which is an ideal situation? I would prefer an FSM with 6% magnesium, 1% rare earth, and maybe 2% calcium, which makes sure that the FSM is calm. The reaction is very calm, not very violent, very less fume generation, and whatever nodularization process happening is to the best. And the inoculation is something that what happens after nodularization. I told you do magnesium treatment. After magnesium treatment, you have microstructure like this. There is no nodules. You just have carbides, very few nodules. But after inoculation, you have a lot of nodules that is formed. So inoculation is very important. Basically, what it does means that it controls the structure by increasing the number of nucleating site. It doesn't create a nucleating site. It increases the number of nucleating site. Magnesium treatment creates the nucleating site. This is all part of graphite management, whereas inoculation increases the nucleating site for graphite growth. So inoculation basically gives nodule count. So inoculation must be added as late as possible. Two-step inoculation is better than one. If you are able to add MSI, metal stream inoculation of 0.2 to 0.7, which is the best. If you're able to add it consistently, then no need to have multiple stages. One is more sufficient. So total inoculation should always be less than 0.4. If you're adding more than 0.4 inoculant after ductile ion treatment, I seriously would reconsider why is that the case. If it is because of hardness issues or nodularity or nodule count, then there is a very high scope for optimizing your process. This is the cost that you are incurring, and most of it is wasted. So do I really need to do it? If I keep my magnesium low, 0.1 of MSI, 0.2 or 0.1 of MSI is more than sufficient. The total inoculation should be less than 0.2. This is an ideal situation. Selection of inoculation is very important. Why do I select this inoculant? Carbon equivalent is a very important area for selecting an inoculant. You don't want to have if you're having high carbon equivalent and you're adding too much amount of inoculant, 0.5, 0.6, the silicon from it is going to affect your carbon equivalent, and you might end up getting oversized nodules, which could result in shrinkage. So carbon equivalent is very important. Keep the correct carbon, keep the correct silicon, and then add the required inoculant. If you're going to reduce your inoculant from 0.3 to 0.1, make sure that the silicon pickup from the inoculant which is being lost due to lower addition is compensated in the base itself. So typically when Elkem goes and optimize inoculant additions, we say reduce your inoculant addition. At the same time, to ensure your final carbon equivalent is the same, whatever silicon loss that is being happening because of inoculant lowered additions, you have to compensate for the additional silicon in the base metal. So you don't overdo it or underdo it. Your base sulfur is also very important. If your sulfur is too low, not only you end up getting very bad microstructure, your nodule count also will be low. Inoculant directly reflects your nodule count. So your treatment process, if it is calm, better. Magnesium content is residual magnesium is low, it is better. So this is a correlation between magnesium content versus nodule count. You can see here, this is the ideal range I would like to operate. If I keep increasing the magnesium, my nodule count will come down. When my nodule count comes down, it opens a can of worms. It can cause shrinkage, it can cause carbides, it can cause slag and dross to get accumulated. So it's a very, very bad situation. Nodule count is very directly correlated to graphite expansion. More nodule count, more graphite is expanding. So more heat is given out. More heat is given out, the metal naturally, when it is shrinking towards the end, gets expanded. So this is the fundamental. So to summarize, maximum yield, you have to go for a low magnesium FSM, preferably 6%. Residual magnesium 0.030, is it really required? Maybe we should operate it at much lower levels. If you're already having 0.030, and I would ideally request that if you're using a 7% grade FSM, think about coming down to a 5% grade FSM and see whether you can optimize your yield. So if you are going to take a casting yield project, I know that with methoding and gating and simulation, you can change a riser big, small, small to big, change the orientation of the riser, keep the riser in the casting or to the side. All these changes can be done. But unfortunately, the simulation software do not capture the effect of inoculation, the effect of graphite management to the extent as what is being performed by the Elkem inoculants. So I would suggest that if you want to have slight inoculation, slight casting yield improvement, you want to remove a couple of risers, you want to save 3-4%, then get in touch with us. We will be able to do that by simply modifying your FSM and inoculation practices. So this is the selection. This I would skip. We have the lanthanum-based FSM that has been developed in 2000. It's not something new. We all know that it is common knowledge that when I use lanthanum-based FSM, my shrinkage gets solved. So how is the magic happening? Either it is the lanthanum that is helping or the magnesium. If you take the lanthanum-based magnesium, it always has low Mg in it. It doesn't have more than 6-7% magnesium. We have lanthanum-based magnesium, interestingly, with 15% magnesium and lanthanum-based alloys in the market, which is quite interesting because the effect is going to be get nullified. I'm not sure why that is being happening, but that's not the right direction. Again, we have coated inoculants. Basically, this coating is with sulfur and oxygen. Why we have? When we see the magnesium, which are metal which is treated with higher amounts of magnesium, it is dead. It is fully carbonatic in nature. Your sulfur is completely lost. You need to have sulfur to make sure that nuclei grows to a respectable shape and size. So Elkem has pioneered this coated inoculants, which is very, very effective when you have when you have high magnesium treated alloys. It is very, very important that you have coated inoculants to at least make sure that the damage is minimized. This I would skip because of time constraints. So to summarize, I have a couple of case studies, but if you want case studies, please get in touch with us. We will be more than happy to help. Quickly to summarize, a 1% casting yield results in savings in lakhs. You can do the calculation. If you are making, you can roughly calculate if 80,000 is your per metric ton cost of production, 1% is 800. So you melt 200 tons and then you calculate how much is the money. It is huge. So carbon equivalent is very important. Moving the liquidus temperature either this direction or this direction either reflects in macro shrinkages or diffuse shrinkages. It's very, very important. And lower temperature is ideal. If you are not able to have low temperature, I would work on having preheaters to reduce heat loss. Base sulfur is very, very important in magnesium selection. A higher magnesium is only preferred when the sulfur is on the higher side. When the sulfur is 0.01516, then I would suggest go for high magnesium. When the sulfur is 0.010, 0.012, then please reduce your magnesium levels. And at the same time, your addition rate also. Calm and magnesium must be as low as possible. When it comes to nodularization process, a calm and long reaction is always the best process. Where you should not even see that the reaction has happened. It should be as calm as possible and less violent. It directly results in a very good treatment with very little spillage. Higher magnesium means bigger risers and more inoculation, which is not very ideal. So in our opinion, if you look at it, these are some of the grades that we have, which is actually having very little magnesium with good amount of calcium and rare earth balance, which gives you not only the best metal, but it gives you the most consistent metal. Also in a sustainability, if you calculate it, the impact of this is very, very low. Lanthanum-based magnesium is going to solve shrinkage, but it has its own limitations. What do I mean by that? Please get in touch with us. Lamattis or lanthanum-based magnesium is not the solution for all castings. Even people who are using lanthanum-based alloy might add 1.2, 1.3 and still not get the shrinkage solved. So it is not, it's not the problem of the alloy not performing. It is not the right application. It is not suited for all castings. It has its limitations. If you want to know more, please get in touch with us. We will give you the recommendation. So when it comes to, as we discussed in the first slide, automation is very important in foundries. So we have very strong FSM or inoculant dispensing systems, which previously used to be imported. Now we have very reliable systems developed locally, and it has been almost successful in all all big foundries who are adopted this. It not only stores the data, it also helps you to control the process. It's quite dynamic. It typically takes out the variation in tapping temperature. It takes out the variation in tapping quantity. It is a very flexible automated system that is available. So if your OEM is insisting to have a data retrieval system or a data storage system, then FSM can also be automated. It's only not to certain types of nodularization process. It is also highly recommended for FSM to have this sort of an automatic dispensers to have this. And when it comes to inoculant, it is always better to go for smaller additions of high potent rather than large additions of ineffective inoculants. Calcium barium based is quite common that it has been outdated. So we have cerium based inoculant, we have coated inoculants which are more potent. When you're shifting to that more potent inoculant, you need to add less. You cannot add 0.4 and then it is not a very economical way to do that. So if you want to have more case studies about how do I improve my casting yield, we have multiple documents. We would like to circulate it. Please get in touch with that. We will not share the pattern design. Pattern is something which is very, very IP sensitive to a Foundry. We will not take any details of the pattern. We will not show patterns of what is being optimized, but we can give you general guidelines of how do we go about optimizing your casting yield. And lastly, I would like to have communicate that when it comes to casting yield optimization from the metal perspective, that is with respect to the chemistry, with respect to inoculation and modularization, we should have a holistic approach rather than simply looking at the unit price. What is the value getting out of it? What is the value of using a low magnesium FSM? What is the value of using a high potent inoculant? What is the value of having a correct carbon equivalent? What is the value of having a thermal analysis system to measure all what we have said? So this is something that we would be more than happy to assist foundries who want to take up casting yield projects. We have a team all over India, and it is not only Elkem team. We have now our channel partners and distributors spread across various foundry clusters, and no customer is too big or too small for us. Anybody having any issues, please get in touch with us. We will be more than happy to help. So I'm going to finish and stop here. I'm being out on time. So if you have any questions, please let me know. And I apologize for being fast. Due to time constraint, I have to swiftly go through without going through the case studies. So this is my content, what I would like to show here. My key takeaway from this is that when it comes to casting yield, 3 to 4% small rises is possible by just modifying the chemistry, modifying your SM and modifying your inoculation. With respect to inoculation, high potent, lower additions. With respect to FSM, extremely low magnesium, 0.5% mg is more than good enough for Indian foundries, and then an addition rate of 0.9 to 1. So please don't follow the trend of having 10% magnesium and having 0.8 or 0.7 addition and expecting to have casting yield, which is not going to happen. At least the knowledge what we have. So thank you all for listening. If you have any questions or comments, I'm more than happy to take.
Anyone has any questions for Mr. Balaguru?
Hello, sir. Hello.
Hello. Hello.
Hi, sir.
Hello.
Is there any specific chart for the as per the casting thickness? How much magnesium percent is required?
We have. I can share you that. You please, hello, Sachin sir, you please get in touch with, you're from Pune?
No, I am from Belgaum.
Sir, you get in touch with Akshay or Pratik, we will give you the details.
Okay, no issue. Thank you, sir. Sir, if we trace the at the base, sulfur is higher up to 0.025.
Yes.
Base sulfur is 0.025. So what we should do?
You should do desulfurization, sir. Desulfurization, either with calcium-based salts, or you can go for magnesium treatments with high magnesium to desulfur, and then do the treatment again.
And if our treatment ladle is red hot and pouring ladle is also red hot, then how much we can reduce the tapping temperature? 1400 up to 1400 we can go. Tapping temperature.
If you're able to tap at 1450, 1400, which is very ideal range. If you're saying that my temperature, no sir, if your temperature at the end of pouring is more than 1300 degrees Celsius and your temperature loss is not more than 50 degrees, then tap at 1350. Whatever is your temperature loss at the end of pouring. On top of that, 100 degrees to 50 degrees is more than enough.
Okay.
Sir, what are the reasons for the violence reaction?
The violence in reaction is because you're having, first of all, not a very correct pocket from a process point of view. If the pocket is too wide, then the metal can come easily lift it, the FSM, and react. The pocket profile is very important. Tall and narrow is preferred, but not so narrow that you're not able to charge the alloy. So it should not be so narrow that the alloy, half of it falls on the other side. The second thing is that the inadequate cover addition. The cover that you add should completely cover the top surface area of the FSM in the pocket. If the cover is addition is too small, or if the shape of the cover scrap is also quite big, which is not an very ideal. So these two are the reaction with the reasons with respect to the ladle why we have very violent reaction. When it comes to the tapping temperature, if it is very high, then also reaction will be very violent. In the FSM alloy itself, when you are having very high magnesium, more than 8%, then then you have extremely violent reaction. The magnesium is high, so it will react violently.
Sir, in the molding sand sulfur. Hello.
Yes, sir.
Yes, sir. The sulfur content in the molding sand is impacting on the magnesium or not?
If you're having the outer surface of the casting, which is in contact with the green sand,
Yeah.
sand with high sulfur, if you're getting flakes in it,
Yeah. So
but the
what is
flakes is
the
not.
so so what is the percentage required in molding sand of sulfur minimum?
I'm not so sure about the exact value, but I can get you the details. From our metal side, if you are having extremely flake in the skin of the casting, one way
Yeah.
to solve it is to use reseed in inoculant in MSI, which is cerium based, which will solve this problem. If the sulfur from the sand is not very high and not for all castings, only for some castings you are having, then
Yes,
I
sir.
would not go change the sand part. It's very difficult to control the sand and the sulfur. Then I would
Yes.
change my inoculant in at least the powder inoculant. If not added, I would first introduce it and I will use a cerium based reseed.
Okay, sir. Okay.
Yeah,
If
0.1 to 0.15 will solve the problem of having flake graphites in the skin of
Yeah.
the casting.
Correct.
if
It is coming in the skin on the casting only.
cerium
You can try
percentage is
reseed inoculant, sir. Sorry.
Reseed
Go ahead.
if cerium percentage is more in inoculant, that is also a carbide former.
No, it's a very interesting
Because
question.
your presentation is one I see there. Ki if cerium is also a carbide former.
Sir, again, what stage you are introducing it? Okay, we are not going to have cerium as a nodalizer, as an inoculant. And how much are we adding? If you are going to add cerium based inoculant after ductile ion treatment, let us say 0.5, then it is not going to be an ideal situation. Too much amount of rare earth is going to again cause a carbides. It also depends on when are you introducing the cerium based inoculant and how much. If you are going for high potent cerium inoculant, it must be added in powder form and it should not be added more than 0.1 and 0.15. In this addition, it only activates the nuclei and grows it to a respectable size. It is not going to cause a problem of carbides.
Okay.
You are adding 0.6, 0.7 of cerium based inoculant, either reseed or any NBA, any competitors cerium inoculant, to solve the problem of having shrinkages, or you want to have maximum nodule count and you're adding 0.6, 0.5 cerium based inoculant, then that's not an ideal situation. When you're going for cerium based inoculant, you should have for lower additions. And cerium based inoculant should only be preferably added in powder form in MSI, not more than 0.15 to 0.2. If it is a manual addition, 0.15. If it is an automatic addition, 0.1 is idle.
Okay.
Sir, what can we do to increase the ferrite percentage for thin castings, like 5 to 6 mm?
Again, ferrite perlite is highly dependent upon your electrolyte transformation and also your elements that is being present. So you keep sure that your perlite stabilizing elements, manganese, copper, and other elements 10 or to the bare minimum, as low as possible. You don't entertain
We are
having
keeping the manganese below point two, below
Hmm.
0.2, where we are keeping the manganese, and copper is traceable, is not too much. Then also we are getting perlite above 30%.
So one thing here is that from the how is this formed is having perlite stabilizing elements. As you say, it is all kept under control. The other way is to prolong the transformation. So that means that can I knock out a bit slow? Can you work on your knockout temp?
It's a Disha high pressure, so it's above 45 minutes.
Okay, then I need to have prolonged knockout time. Either modify by methoding, or I see there is two aspects of controlling a ferrite. One is to control the perlite promoting elements. Other thing to have prolonged cooling. What happens is that at eutectoid, all graphite nodule will act as a sink of carbon. So your nodule, if you see after etching, the surrounding area of the nodule will always be ferrite. We call it a bull's eye. So what does a nodule does?
Yes.
It basically pulls the carbon towards it. So if you want more perlite, when you add copper, what does the copper does? It forms a ring around the nodule so that the dissolution of carbon in the surrounding area of a nodule is not happening. But in case of more ferrite, what we have to do is that we want that dissolution to happen, right? So all the carbon that is in the matrix as carbide must dissolve and go into a nodule. So to make sure that happens, you need to either reduce all your perlite promoting elements, or you need to increase your pouring, you need to increase your knockout timing. So these are the two directions in which you have to think about.
Okay.
But if you want any guidance, please let us know. You contact your nearest Elkem representative. We will come and see, collect samples, see what we can do.
Okay, sure.
Maximizing nodal count can also help. So we will be more than happy to help there.
Okay, sure.
Yeah.
Sir, how do we determine the riser size without risking shrinkage effect?
How do we determine riser size?
Without risking shrinkage defect.
So first thing, I would look into the profile of the casting. What is your gating for it? Okay. If the gating is good, it is following all the norms and standard SOPs that is being maintained. Then I would see what is my chemistry. If I have the correct carbon equivalent, if I am in good FSM and inoculants, then I would not even consider having a riser there. So your question of having a chart, basically if my mg is this much and riser should be this much, you can refer to Soral Metal details, because we are not very big on riser calculations Elkem as such, but we can guide you on what should be the level.
Okay, sir. If no more questions, I'll move forward with a vote of thanks. On behalf of Institute of Indian Foundrymen Chennai chapter, I extend a sincere gratitude to all those participants for joining us today. Webinar actually on Elkem's Ingenious solution actually for increasing ductile iron casting yield. A special thanks to our esteemed speaker, Mr. Balaguru Sendil, for sharing valuable insights and practical knowledge on ductile iron casting yield improvement. The session was highly informative, and believe the learnings will certainly support our members in enhancing process performance and productivity at the respective foundries. Last but not the least, thanks to all the participants for your time, active participation, and continued encouragement for all the technical initiatives. We look forward to seeing you again actually in the upcoming programs. Thank you and have a great evening. Thank you.
Thank you.
Thank you. Thank you.